Okay, so today we're going to do this first thing we're going to do is do this improving the presentation of a sheaf. So remember the situation. We have a sheaf given by m tilde for some module m, and unfortunately the m is not uniquely given. Okay, so this is going to be another formula also for computing cohomology, but the main use that we'll put it to is to calculate better presentations. But anyway, here it is. Let's see if I can keep this. Seems to. Well, whatever. Okay. So anyway, so we start with the finitely generated graded module like usual, and one of the numbers that is going to be useful is the Castelnuovo-Mumford regularity. So let's see what that is just in this case, or in general. I take a free resolution of my module M. Nice finitely generated graded module. It goes some distance out. And I keep track of the degrees everywhere. And at the ith step, I have a bunch of degrees. They're always going to be negative. Well, actually, they're not always negatives. But I'm going to write them as negative aij. The aij's actually could themselves be negative. Okay? So I have all of the degrees throughout. And what I do is I take the maximum of the at the ith step, I take the maximum number that occurs, aij, and I subtract off how far back I am in the resolution. So at the f0 step, for generators of m, I don't subtract anything off. I take the maximum degree of a generator of m. That's the maximum for f0. Then I take the maximum of a degree of a first syzygy, those are the f1s, minus 1, and I do the same thing. I keep going all the way back until the end, and I take the maximum of all those possible numbers, and that's the regularity. Now let's see. Unfortunately, let's see, this slide, the regularity, if we take the rational quartic, let's remember what the numbers there were. Where are those the pens? I got other pens here.
Sorry, Mike.
That's okay. I got one. Okay, so the numbers I'm going to just write on this were s. Make sure I'm writing on this. So it was s of minus 2 to the plus s to the minus 3 cubed, s to the minus 4 to the fourth, and then s to the minus 5. So the maximum at this last step here, this has a maximum of 3. This is maximum 4 minus 1, and the next one is 5 minus 2. Those are all equal to 3, and so the regularity of the ideal is actually regular. Yeah, this is this is of the ideal here, because the next step over is just the ideal. If I go to S mod I, all the numbers are shifted over by 1, so I have to subtract 1 more. So the regularity of I is 3, and the regularity of S mod I is 2. Okay? So this is a cool number. It comes up all over the place whenever you're doing any sort of computational algebraic geometry or non-computational stuff. And now here's the theorem of Serre. He doesn't usually. This is all the same paper, right? His fact paper in 1955 and so on. Although the regularity statement's not there. But anyway, it's not so hard to show that. So anyway, suppose I take any integer I, and I take L to be large enough. And by this, I mean this I here. And actually, I could be a lot more precise in certain situations as well. But anyway, so for L large enough, the cohomology module, hi of m, the star, I am truncating it at degree 0 here. Just got to truncate it somewhere because these are oftentimes not finitely generated. That's actually equal to another x module, which is not quite of the kind we've actually seen so far. The j sub l is just the powers of the variables to the nth power. And so I take that x of that ideal into my module m, and I have to truncate them both at the same point if I want them to be the same module. Okay? So here we have another description of how to calculate hi of m tilde in any given degree. Okay? By the way, how do you prove this? I forgot to give show you how to prove the local duality, but it's all the same kind of thing. What you do, and for this one, is you check the statement if M is a graded free module. Okay? Pretty easy to do there, because everything is just almost always just trivial, but you need to have, it depends on the degrees that you have. So you check that, and you can prove it there. And then all you do is induct by the projective dimension. And you just use exact sequences and the 5 lemma out the wazoo, and and you got it after a little bit of time. But certainly, if you want, you can do that in a locked room and still be able to make it for lunch, probably. Tomorrow. Okay. So anyway. Now, the main use of this, actually, is that we will use is when I is 0. This is finally a case where we actually are getting H0 of M tilde, as opposed to the local duality, which gave us it up to some extension. So this is actually very good, and so we want to consider this situation. In that case, I is 0, so we have to take L to be a sufficiently large integer, but is that on there? So now I'm going to talk about improving the presentation of a module. So we've got some module, and we'll do an example in a bit also of it, because you have to sort of see it. Suppose the projective dimension of your module is less than or equal to n minus 1. Remember the possibilities. It could go up to n plus 1, n minus 1 or smaller. If it's n minus 1 or smaller, that means that from the local duality, M was actually the same thing as H0 lower star of M. So you had the whole module in hand already. And that was good. Sort of the general philosophy is that's the best possible one that you will find. I suppose it's always possible that you can find something else that it has a simpler presentation that it doesn't satisfy this, but usually I've not actually seen that ever happen in practice. So you can't really improve it. What if it's at the very end? What if it goes all the way to the end? Excuse me. Well, let's suppose that you write your module as a quotient of a free module. So it is given by generators and relations, F modulo I. I is not an ideal. I is a submodule of the free module F. Well, you can do this so-called saturation of I, which is this following notion. You take I, you take it's called colon of the x0 through xn infinity. What that really is it's a set of elements in your free module F such that some power of each xi times that element lands you back into your ideal I. Okay? And then it's actually pretty easy to check that I sat and I give you the same sheaf, and actually so do the F mod I and F mod I sat. And what you get from this now is that this thing has projective dimension less than or equal to n. Once you've done this, you've dropped the projective dimension down. It's not less than or equal to n minus 1, but it's still not bad. And this saturation here is a reasonable thing to do in a computer algebra system. It's again a Grubner basis calculation or a syzygy calculation. There are several ways of doing it. It's a little bit of an art form to get good ones on hard problems, but in any case, that's what you have. Any questions on that so far? So far, yes?
So is I, you said that I was not an ideal, but is I sat that is an ideal? Or
No, I sat is a slightly potentially larger submodule of F than I. So you have actually, the case when F is the ring, S, is an interesting one as well. And then you have an ideal I, and then you have its saturation. And actually, the Hilbert scheme thing I mentioned, what it really parameterizes are saturated ideals, things that are their own saturation. But it works for some rules also. Okay, yes?
So for the first case where you said for the projective dimension is less than equal to n minus 1, then you said you can't improve m if it equals h0 star of m. Right? So is there does h0 star of m have an obvious sort of free resolution by...
So the question is, does h0 lower star of m have a nice free resolution? And the answer is, the answer is yes, it does. It's going to be of length less than or equal to n minus 1. At least if it's finally generated.
Is it just sort of check complex? What does it come from?
It comes from the fact that once you have m and m lower star, then the xn and xn plus 1 both have to be 0 because from that local duality statement, and consequently the projective dimension has to be smaller than that because it's the projective dimension is the largest of one of those things. You can probably get it from a lot of other things as well. Okay, so here's the situation with projective dimension. It's supposing that it is equal to n. So you actually improved it here, and you get it down to n, and that's very nice, except that you could actually do better now. So the x0 is really Hom from the approximation theorem. And so if you take L, actually if you take any L whatsoever, this homomorphism module will have the same sheaf as M. But if you take L to be as large as what I had, as large as the regularity, then in fact, as long as it is really going... Well, let's see. You have to be a little careful. You have to take L to be large enough, and then you're going to get H0 lower star of M truncated in degrees greater than or equal to 0. But that might not be the whole thing yet. Okay, so at some point, if it's finitely generated for large enough L, you will get the entire module, and then that will be the one that has projective dimension n minus 1. But still, even if you don't do that, this can still be a better presentation. There's one little problem with this whole thing, is that if you actually need to find this value regularity of M, the trouble is you might have a really nasty module that you started with, and calculating the free resolution of it to find the regularity, which is about the only way, is a problem. But it turns out if you instead take the initial lead terms and you resolve that, you'll get a slightly larger number, which is much easier to compute. So I didn't write that down, but you have various tricks at your disposal for this kind of thing. Okay, so what I want to do is a simple example. It's actually the example I was sort of working on last time. Okay. So here we have just a quintic threefold. And I want to consider omega 1 of x the second power of omega 1 of x. Remember this had to do with this rationally connected conjecture. And I want to calculate this. So last time we figured out what omega 1 of x is, and all we have to do then is tensor product it together. But tensor product is one of these operations that tends to give you bad presentations. Okay? So we're going to take a look at it. When I do the tensor product here, what I get is I get 100 generators that are of degree 4, and I get 300 relations, some of degree 5 and some degree 8. Okay? It's not really so bad. The reason I'm choosing the Fermat quintic here is so that we can actually do this calculation, and so you can sort of see how it gets better as we change it. If you take a random quintic, which you can do as well, then the free resolution of this thing becomes, shall we say, a little harder. Okay? Whereas once you improve the thing, it will be a lot better. So actually, let's see if we can get this on now. Okay. What are we doing here? Any questions while this is going on? So our plan, oh, why is that so small? Sorry, I forgot to change the font. Was this large enough? Oops, that's not what I want. Is that okay? Okay, so let's actually do this. So this is the omega function we had last time. I'm just redoing it. And here's the polynomial ring in 5 variables. So that's the coordinate ring we're doing. And there's the quintic. And here's the presentation of omega of I. Actually, this is smaller. Can you really see this in the back? The way you have done it in the past. Here's the tensor product of omega x with itself. I put a semicolon so we don't have to look at it. But we can. The Betty command tells you how many things there are. And sure enough, there's 100 generators and 300 relations, is what that tells us. It tells us the degrees, too. This next command is going to do the first kind of improvement using the saturation. It's a little complicated the way it writes. Can you actually see this way down at the bottom? I take OM2 is the tensor product. I take its presentation, and I take the image. That's the submodule that we were talking about, the I that we had. I saturate it. That does exactly what we said, the I colon all the variables to the infinity. That gives me a submodule. I take the generators of that submodule and co-kernel, because I want really F module of that thing. So this does the whole bit in one line. I should have hit the return. Oh, I guess I didn't take that long. And now here's what it comes out to be. The way it improved it is there's still the 100 generators, because actually the saturate doesn't ever change F. Okay, so that's always still there. However, we now are down to 230 relations. It looks somehow almost worse, but because there's some element of much higher degree, and that can happen. Okay? But it's perhaps a little better. The 5 at the top, those 5 are actually linear terms, so it will kill 5 of those 100 generators. So there's actually 95 generators of this module. Oops. So now we can resolve OM2, and this is what the free resolution of it looks like. 100, there were 280, actually I said there were 300, but I guess that wasn't a minimal set that it gave me. There are 289 relations, and then it sort of goes on back. Okay? And now, instead I can resolve the saturation. Notice that, by the way, it goes back to step 5. How many variables were we in? We're in 5 variables, right? So that's all the way to the back. So it has the non-saturation, so that this one should improve. And sure enough, it improves 100 to 230. It's just a lot simpler in many ways, and it goes one step further back in the thing. So it's just a better presentation. And if we look at its generators, it doesn't look that much better necessarily here, but there you have that. Okay, now we can take the so-called, I call it OM2 depth 2, projected dimension less than or equal to n minus 1 is the same as what depth 2. We haven't talked about that, but we're not, anyway, whatever. Here's one way to compute it without having to go through and do it all by hand. I take the sheaf corresponding to my tensor product. I take H0. There's a greater than or equal to 0, which is doing the truncation in that and giving you the module back again. Okay, so when I do that, I should have hit return, because this one I think might take a little bit of time. I can't remember. Well, that wasn't so bad. Okay, so here is this one now has, this one totally changes the presentation. So now there's 61 generators and 106 relations. I think those are minimal. We can take, that's what we started with originally. And now we can do the resolution, and the resolution now is even one step shorter. And so this is really the whole cool thing, and it's 61 by 100. Yeah, it's just sort of a little easier to deal with. Then you could, if you calculate the x modules for each of these things, though, it really should be pretty much the same thing, although it doesn't have to be, I guess. Anyway, this is not useful. So you can do that and then look at the dimensions of these things. I do have the dimension of it around here somewhere. Oh yeah, the Hilbert function, this is giving us h, this is x3, so I'm actually calculating one of the h, I think calculating the h1 of this, of this tensor product sheaf, and you get that it's 101 dimensional. I guess that's right.
That's h1.
Yeah, that's right. So, except that it's really omega 1 tensor itself, not wedge of it. So there's it's a little fishy. But it's, you know, so anyway, so there is this sort of thing here. Okay, we'll leave that for the moment. Now what I want to do in my remaining hour and 50 minutes is apply this to studying line bundles and divisors and things like this. So so let's just recall a couple things about this. Okay, a line bundle on X. So X is now our projective variety or whatever. Actually, I'm going to take it to be a smooth projective variety. We can do it for normal things or a little more generally, but you have to be a little more careful with things. All it is it's a coherent sheaf that is locally free. In other words, there's an open cover such that when you restrict to it, you get a free module of rank 1 on each of those. And the key example is the following. If I take X to be a smooth, actually that one is true anywhere, but if I take X to be a smooth variety, and I take an irreducible codimension 1 subvariety of it, it has some ideal J contained inside of R. Since it's smooth and so on by various properties like the various things, you can show that this thing is locally generated by a single equation, which means that it will be this ideal J tilde is going to be a line bundle, locally free rank 1. That's usually called OX of minus D, or as Hartshorne would put it, script L of minus D. But you can also get OX of D, which is the dual of that. And the way you get that is you take Hom over the ring R, not S. This is one of the situations, what we're doing today, where it matters whether you're doing it over R or S. So we're doing Hom over R of J into R, and sheafifying that, taking the sheaf associated to that, and we get this, this line bundle OX of D. Okay? So these are the cool ones that we're mostly interested in. There's also the notion of divisor. And just to sort of recall this, is that, what is a divisor? All it is it's a formal sum of codimension 1 irreducible subvarieties. So for curves, it would be a bunch of points. So in any case, we have D as a finite sum like this. And you can build OX of minus D or OX of D by using the following properties. So suppose I have already constructed OX of D somehow or another as M tilde for some module M, and I've already constructed OX of E as N tilde, where M and N I think of as R modules. Okay? Then I can construct OX of the sum of these two divisors, or the difference, or the negation. And here's the general way. To take the sum, I could take the tensor product of the two, just like we were doing before, and take the sheaf associated to that. That one tends, just as a general practical thing when you're doing this by computer, that one's not the best possible because this tensor product gives you bad modules. The next one, Hom of M into R, that one is really good usually. Hom, it sort of makes presentations better. Okay? So OX of minus D is actually going to be have a better presentation than if you do it some other way. And if you want to do OX of D minus E, you can actually combine these two things. You can do Hom of one into the other. And I think I got the direction right. I sort of, it should have done E minus D, the hum M in, but this is correct, I think. Okay, so basically, you can either think of divisors or you have these sort of associated line bundles or sheaves. Well, it's not the case that the line bundle or these M tildes actually determine the divisor D, right? In fact, in algebraic geometry, this is called linear equivalence when this happens. This is not necessarily the way you would first run across the definition of linear equivalence, but it's not a bad way, okay? D is linearly equivalent to E if and only if their corresponding sheaves are isomorphic. Okay? You know, okay, so it leaves a little to be desired from an elementary standpoint, but in any case, that's the same as saying OX of D minus E is the trivial sheaf, O of X. Not, well, trivial, you know, the structure sheaf. That's actually very cool because that's something that we have some chance of really testing. So in fact, let's do this. Suppose I give you an R module, and I want to know whether its sheaf, the corresponding sheaf M tilde, is O of X. How do I do it? Well, I can find this H0 M tilde by using the theorem that we had before, truncated in some degree. You can see that this slide got written after Bernd suggested the greater than or equal to 0 notation, where it is. But in any case, so what you can calculate that, and then if you're lucky, that will be your ring R right off the bat, exactly. Okay? But you know, you're not always lucky. And the trouble is that H0 of R tilde might not be R itself. It might be larger than R. And so if it is equal to R, you're going to detect it immediately to see whether this is the case. And otherwise, you have to check whether these two things are the same.
Mike, just to kind of reboot, so could you give a simple example of an R where this is not R?
Yeah, so probably a simple example is the rational quartic. The rational quartic curve has H1, it has this H0 of R tilde. Remember, it had this extra little copy of K. And maybe when we get back on the computer, we can actually type it, figure out what the H0 of this is. But basically, it has one more generator. So it's generated by two guys, the one in degree 0 coming about from the ring, and then another one in degree 1. Okay. Any other questions? Okay, so we'll play around with this a little bit when we finally fire up the computer again, but let's do a couple other things first. How about divisors on a curve? Okay? In this case, a divisor on a curve is a very simple kind of concept. It's just the sum of points with various multiplicities, ni. The degree of a divisor is just the sum of the ni's of that. And what about this number? That's the degree of a line bundle. Riemann, because he actually had some modules in hand and wanted to be able to calculate the degree of the corresponding line bundle associated with that module, very carefully made the following function. Actually, rock, I suppose. The degree of L, if L is the line bundle associated to M, or there's the sheaf associated to the module M, then the degree of that thing, which is the sum of the number of points, which will be the same for any D that gives this L, is the Euler characteristic of M, or M tilde, minus the Euler characteristic of the ring R, or of X. So that's just, remember, coming out from Hilbert polynomials. So that's an easy thing to calculate. And basically, Riemann-Roch is giving you a computational algebraic geometry way of calculating the degree of a line bundle on a curve. Okay, well, maybe that's not the way you always think about it. But you know, actually, the degree of a line bundle isn't the most trivial concept in the world if you start looking at topology. So the next thing, we're not going to actually do an example of curves in this just because of time. But we will do one of surfaces. I want to sort of talk about divisors on a surface. So, okay, so here we have a surface X, smooth projective surface X, or maybe normal or something, depending on how general you want to be. And you take two irreducible curves, C and D, on X. They don't have to be smooth or anything like that. The problem is to find their intersection number. Okay? Well, if they are different curves, it's pretty easy. You can just count the number of intersection points. But we're interested in all curves, so we want to know what also happens if they're the same curve. And if you can move one of the curves in its homology class, right, then you can, so that they're distinct, then you can count the number of intersection points with multiplicity, and that's fine. But a lot of curves won't move, and so you're kind of stuck. And there's lots of ways around this. You can rewrite the divisors as the sum of two different, one minus another, where all of these are different components, and you can you have these moving lemmas and things like this. But here's another way of doing it, which is essentially Riemann-Roch for surfaces. So let's suppose that M tilde and N tilde are the line bundles corresponding to divisors C and D. So that's the OX of C and the OX of D. And we calculated them using one of the other things here. Then you can take the intersection product of these things. This will be the same as, I should have said, C dot D. And it's the Euler characteristic of O of X minus the Euler characteristic of one of the M's minus the Euler characteristic of the other, plus the same thing for the tensor product. Okay. And so that's a good formula. This, by the way, works in higher dimension too. You can do it for threefolds by intersecting three of these things, and you have all the possible combinations of pluses and minuses. Let's see here. What are we doing? Okay. Here's an example that we're going to do by computer in just a bit. We're going to do two more examples in this set of lectures. One of them is this thing, and then the other one is going to be a mystery surface where we don't have it easily set up at the moment. But here what we're going to do is just take some cubic for Roth cubic. And the reason I chose that particular one is we know that there are always 27 lines on these surfaces. And I just chose this one so that we can easily see some lines on it. We don't have to do that. But so L1, for instance, is just where I say A plus B and C plus D are 0, and so on. Okay? And what we're going to find by computer in a bit is that by doing this kind of thing, you actually can get these intersection numbers, L1 squared, L1 dot L2, and so on. L1 dot L2 should be easy. Do they intersect is the question. Do they? I have to intersect on the surface, and they certainly do. Okay? So, and there are two lines, so they'll intersect at one point. Okay, here we'll save the rest of that a bit. So let's actually just do this thing for fun. And while that's getting ready, any questions? So basically, what's cool about all this is that divisors are something that you can really use to sort of take a variety and play around with it and try to really figure out what's going on it. Also, I think it would be, this kind of thing is useful also number theoretically, although you have to tell me. So now, here we have, let's go to this one. Okay, so first of all, I'm going to start off by making a function called intersection. I can't use intersect because that's for intersecting ideals and things like that. So I do this. I take the Euler of the ring of M minus the Euler of M minus Euler of N plus the Euler of M times tensor N. And that's exactly the intersection product that we were doing before. So that's a function. And now let's actually just make our polynomial ring and our Fermat cubic. And R is R, S, I. These are all our standard notation. And L1 is one of the curves that we have up there. L2 is one of the other ones. Okay. Now I'm going to make those are the ideals of those things. And notice they're ideals in R, the way that it's set up. That's the quotient ring. I'm now going to calculate HOM of that ideal into R, and that's going to be the OX of L1 that we had before. And I'm sort of doing that because you get something a little more, you get an image thing here. And O2, I also get an image. But anyway, I get some module, and however it comes to you. I just want to get it slightly away from being just the ideal, so you can see it. Now we can intersect it by taking these two modules, OOL1 and OOL1, same thing, and we get -1. So that says that the curve, the line, if you're familiar with all of this stuff, you know that all the lines are rigid. There are 27 of them, and they can't move. If they could move, then the intersection would have to be greater than or equal to 0, because you calculate the number of points of intersection of two things. But since it doesn't move, it can be negative, and sure enough, you get -1, and that's basically saying that this thing was a blown up, a blow up of a point. Let's see, intersect module of L1 and module of L1. This is doing it without doing the dual first. And that should be the same thing, because the intersection product is linear. And sure enough, it's -1. We can also intersect L1 and L2, and we get 1 as expected. This is probably complete overkill to figure that piece of information out, but in any case, sometimes it's not. And L2 and L2 is also a -1 curve. So it's also genus of L1 is 0, genus of L2 is 0. I want to avoid this next part for the moment. Okay, so that's enough of that for now, I think. Let me see if I have any other things that I want to say. Oh yeah, so let's do this other thing here. I'm going to take the ideal of A plus B plus C plus D. That's a hyperplane, and I'm going to add it. I'm going to intersect I with that, and I'm going to decompose that. I get 3 lines, the 3 lines that we talked about: L1, L2, and L3. Okay. Now I'm going to let L3 be the 3rd line that I hadn't defined before, and I'm going to let OOL3 be the corresponding OX of L3. Okay. Now here's what I'm going to do with it. I'm going to tensor product all 3 of these together so I can get O of L1 plus L2 plus L3. That should be, since this is a hyperplane section of our surface, this should be linearly equivalent to 0. Okay? So let's see if the tensor product, Bernd, do you think the tensor product will right away give us the ring R?
Probably not.
It's nowhere near the ring R, okay? In fact, there's no way that it could possibly give the ring R off the bat. Okay? So we could try to improve it by either doing one of the 2 ways of improving it that we talked about before. One way, in this case, I think it doesn't matter, so I'm doing the first one, where we just do the simple saturation. Yes?
Did it say again why the sum should be 0?
So if I take a hyperplane section, and I have 3 lines, it's actually 3 lines in a plane. And basically the sum of those things has to be linearly equivalent to, actually not 0, to the hyperplane section. And so in fact, actually, it's not going to be, it's going to be 1 off from being trivial. So I guess I misspoke, so that's good. You caught that. Okay, here is the saturation of this thing. And it's also a bit of a mess, okay? So it didn't really do it. We can't tell whether this thing is the ring twisted by 1 because of the H, okay? That's what it would be if it were the H. So instead, I'm going to lift the presentation of this module back to the ring S, because I want to use the other way of improving the thing. Actually, I want to calculate the resolution first. The resolution, this is the one of the improved thing. It has length 3, which is not short enough. We're in 4 variables, so we don't have the whole H0 lower star. We have to have length 2 of the resolution in this case for that to be the case. So I'm going to take the same thing that we did before. I'm going to take the sheaf of this thing. MS now is the tensor product of the 3. I improved it a little bit. I could have used the original one. And I'm taking the whole module of where I truncated 0. Okay. remember it taking that long. Look, it's the co-kernel shifted in degree by 1. That's the hyperplane section of the co-kernel of a cubed plus b cubed plus c cubed plus d cubed. That is exactly the thing. So it's saying that those three things are linearly equivalent to h. And so consequently, here you can look at the sheaf if you want to make sure you got the dimension right. It's a quotient of O of 1. So it's really OX of 1, which is the hyperplane section. Okay, is that all I wanted to do for that one? Yes. Okay, good. Any questions on that?
Did you have to lift the S to get that to work right? Why couldn't you have made that computation in R?
I could have done it in R. What I couldn't have done in R was actually calculate the free resolution to see if it would help to do it. So the reason I calculated the resolution is just to show you that it wasn't quite the whole thing yet. But I could have just not done that. I notice I did it in 2 stages. Sometimes that's good, sometimes it's not. It's an art form. So, any rate, let's see. We started at 5. So we have about. We started actually about 7 after.
Keep going.
Now, the next thing that's important, the one thing we haven't actually talked about at all yet is the canonical bundle, which is probably the most important of all the line bundles on a variety. Oops, I did the wrong one. But anyway, it doesn't matter. Here's a statement of Serre-duality, which one can actually prove. Well, in any case, we're not going to prove it right now. So if X is Cohen-Macaulay, this doesn't mean that the coordinate ring is Cohen-Macaulay. It means locally it's Cohen-Macaulay. For instance, it's of a smooth variety. Then there exists a locally free sheaf, actually of rank 1. It's a line bundle, omega x, such that for any locally free sheaf f on x, that the ith cohomology of f, you can also calculate as hd minus I, d is the dimension, of omega x tensor the dual of f, where f dual is just a hom of f into O of x that we sort of saw it before. Okay? So this is a statement of Serre-duality. And actually, with everything we've done now, the proof is also not so bad. Probably not time before lunch, but in any case. Here's a restatement of that statement in the following way that actually makes it useful for computation. So notice that hi of f is this. Well, I can also look at hi of f twisted by d, for any d. D is a bad number here because that's somehow turned into the dimension as well. That's a little unfortunate. But in any case, so say twisted by e, okay? So hi of f twisted by e, how does it change on the f star? Then the f star will be f star tensor with O of minus e, which is good because that actually is, well, you're going to get this formula, and I'll show you how to get it in a second. That if I look at the module corresponding to this dualizing sheaf, omega x, here's one way to get it. There's other ways, you know. I could have taken the highest exterior power of my omega 1. But that turns out to be a sort of bad way to do it, at least computationally, because you get a very bad presentation, whereas this one tends to be very good. So I take x to the codimension of my x, S mod I into S of n minus n minus 1. No check, no twisting it upside down or anything. Right on the nose, this is it. And the proof is actually pretty reasonable. But let's, the real statement here then, of course, is that omega x is that module that I had up there, xc of S mod I, S n minus 1. Take the sheaf of that, and that's my canonical module. Okay, and the proof is just unwinding the things that we had. You can see it here if you want. Serre-duality gives you this statement down here in green, which is what I was just saying. Unfortunately, it's a little unfortunate that there are a lot of D's floating around. So I somehow didn't notice that. So this one here will be an E, and this one here will be a minus E. Okay? And when you take the direct sum of all those things, you get that statement there. You have to worry maybe a little bit about the module structure, but not so much. And then once you have that, that says that h0 lower star of this thing, if I plug in f equals to omega x, is hd of O of x. Check. But by the other theorem that we had, that thing check was exactly xc. So all the checks just go away. So that's kind of good. Now, as an example of this, we're going to consider the following situation. We'll do it in a bit. Suppose I have a surface now. This is true in general, not just for surfaces, but also for curves, and it's just a generally useful thing. Here's an example for surfaces. If I take a smooth projective surface, x, then I can decide if it is rational by looking at two cohomology groups. I think I mentioned this in the first day. If I take h0 of the tensor product of omega x with itself, which is the divisor corresponding to twice omega, or 2 times the canonical divisor, if that's 0 and also h1 of O of x is 0, then my surface is rational. Okay. So now in the remainder, I want to do a couple. Now I don't have that much more to do. But at any rate, we want to look at a mystery surface. Okay? And I'm going to give you the equations for it right here. So, but before I do that, let me just tell you, it's going to be a surface in P4, just to sort of get you oriented. We'll calculate that it's codimension 2, which is surface. It is also smooth, although I didn't bother doing that. It happens to have degree 6. And then we're going to calculate the canonical bundle and look at its intersection numbers with itself, which is sort of good pieces of information. And then we'll find out that it's a rational surface, and then maybe we'll say something else about it. So let's do that. Let's see, while that's going, let me just search things here. Okay, good. Well, that's going. I guess this is another time, a good time for a question until that comes up. Any other things here? Things you'd like to compute about these things? I mean, actually, there's a lot of things about divisors that one might be interested in. If you're familiar with divisors, you might realize that you can also calculate with linear systems or maps to projective space, figure if things are ample or very ample, all of this sort of thing. And this is all, in principle, possible. Okay. So let's get rid of these things for a moment. And we'll actually try to compute down to the point here for the moment that this thing is rational. And then we'll see how to use that. Okay, mystery surface. I'm doing this, I did it over a finite field just to keep it a little shorter. But anyway, it's in P4. There's my ring in 5 variables. Here's my ideal. Okay? That's only part of it. I sort of did this randomly. So here's the first polynomial. That's that. Okay? Then the second polynomial is long. I didn't bother breaking it up. There's a third polynomial, a fourth polynomial, and that's it. If you look at it, they're all cubic polynomials. So it's generated by 4 cubics. Its codimension is 2, as I promised, and its degree is 6. So I have a surface of degree 6 in P4. Anyone have a concept of what this is? Let's take the quotient ring, and let's figure out a little more. Okay.
How about syzygies?
Yeah, okay. That's going to give it half away, but okay, so. We'll do the syzygies in just a bit, okay? So, so x2 of s flat I into s of minus 5. This is the canonical module. I think of it, instead of omega, as k, right? And I do that, and I get the co-kernel of some matrix. Actually, there's 4 of these terms here, and it's a 3×4 linear matrix, which is... So actually, as it turns out, this ideal is actually the 3×3 minors of this 3×4 matrix. Okay? So it's a Cohen-Macaulay codimension 2 ideal. But it's still got interesting geometry, even though it's sort of pretty simple from an algebraic point of view. Okay, let's calculate H0 of k. Why am I calculating H0 of k? I don't know, just because I felt like it. So now I'm calculating the intersection number. I'm actually calculating and seeing if it's equal to -1. Oops. I don't know what I hit, but anyway, it's true. It is equal to -1. So k squared is -1. If this turns out to be a rational surface, what does that tell us? K squared of the projective plane is 9. Every time you blow up, you drop k squared by 1. So this would tell us, since k squared is -1, that we're at least blowing up 10 points from there, and then possibly more, and then blowing stuff down. So we'd have to figure that out. So it's already telling us quite a lot of information. I can intersect k with the hyperplane section. This is a little messy the way it looks. K is intersected with the tensor product of S mod I with the shift by degree 1. By the way, all of these things for the lectures, I think we're going to put in, we'll copy as well with the lecture notes. And this is -2. Okay, whatever that tells us. Okay, tells us that well, it tells us a lot. So now let's take k squared, k tensor k. This is the one we were interested in. This partly because we're interested in whether we want to use Casanova-Nova's criterion, and we get something. We take its resolution, and it's relatively nasty, actually. We can take, but we don't care if it's nasty. In this case, I think we can just calculate it. I'm going to take H0 of this thing, in any case, and it's 0. So that's one of the two pieces of information we needed to check rationality. The other one is H1 of O of X, which is H1 of the sheaf of the ring R, and it's 0. So this is a rational surface. It's a smooth rational surface. Yeah, so Casanova-Nova's criterion is basically these two things here. If I take omega x, tensor itself, that's K2 here, then H0 of that has to be 0. The second condition is H1 of O of X has to be 0. So these two guys here, if they're 0, then the thing is rational. Okay? So it's rational. Oops, I don't want to do that yet. Although we don't have that much more time. So actually, if you, in fact, we'll leave it at that. But what happens, you can actually figure out rationality. The way that the Casanova theorem works, and I'm just going to state this because we don't have time to sort of do it, the way it works is that you use this information and it picks out a curve on your surface that is rational and smooth by using the numerical information there, which you can actually do by computer. I have it on the slide. It'll get copied so you can see it. Okay? And so you can actually get a curve. In this case, it turns out to be a rational quartic curve. And it has a positive self-intersection. C squared of that is 1. And that's enough to sort of sweep it out. And actually, if you then embed using that linear system, if you're familiar with this, that's the map to P2 that blows down the 10 points. And this is what's called the Bordiga surface. So there's the criterion, and here is the surface. Okay? So actually, this surface is blown up, P2 blown up at 10 points. It's embedded by 4L, by quartics through those 10 points. And the canonical divisor is actually -3 times the pullback of a line on P2 plus the 10 points. And the map from X to P2 corresponds to that rational quartic C that I just talked about, and which you can actually calculate. Okay. One more slide, since I left out 1 or 2 slides that you'll see if you look at them. Okay, last slide. Okay. Okay, Stillman, what did you leave out of this lecture? Okay, so the more appropriate question, I think, is what didn't I leave out? Okay, so first of all, there's all sorts of cool stuff on divisors that would be one could really do. Here's a few things that I had in mind. I still remember when first gave a note of what I was going to do in this. I think I had everything that I've done in these 4 lectures in probably the first half of the first lecture on my... Anyway, I was a little optimistic, I suppose. So the first thing is this, there's another way of getting cohomology, which is using this Berenstein-Gelfand correspondence, which is done extremely explicitly by Eisenbud, Feuchtstadt, and Schreier, implemented in Macaulay 2, and it works quite well to figure out homology. It actually gives you other kinds of information than what we've talked about. It gives you a great way to construct varieties with certain properties, homological properties. The next thing is global X. I've mentioned this several times. You can get global X of the sheaves M tilde and N tilde as a usual X, where you have to truncate the first module in some degree D, and then take the degree 0 part of the resulting thing. And Greg Smith has a nice paper where he describes precisely the D and has nice proofs of this fact as well. David Eisenbud, Mircea Mustada, and I have this also this generalization of these results of Serre for doing it for toric varieties, which are quite useful as well. David Eisenbud and Frank Schreier also show how if you have a map, a projective morphism from X to some affine thing like this. So it sits inside a PN cross spec of A to spec of A, say, you can calculate the higher direct images of coherent sheaves. And this is using the Berenstein-Gelfand correspondence. You can actually do better than that. You can get complexes that actually map that represent it in the right category. Okay, so there's that. And actually, there are a couple of things I didn't mention. There's one is that there's this really cool relationship with D modules. So D modules is the Weil algebra, and you can calculate. You know how I said these HI lower star of these sheaves are not finitely generated? Here's a really cool thing. They actually have a D module structure. So remember that the D module is you have variables x1 through xn, and also dx1 up to dxn, and it's a non-commutative thing. Well, it turns out those things are finitely generated over that non-commutative algebra, and you can actually compute with that as well. It's a little harder to get minimal presentations of things, but still it's pretty cool, and you can use that to get other kinds of cohomology in nice non-projective, non-coherent cases that we're talking about here. Yes?
Maybe one comment. So in characteristic P, you can use Frobenius instead of the D model.
Right, that's right. Anyway, so there's a lot more that could be said, but, you know, got to stop somewhere. So that's it. Thanks.